Hello and welcome back. The next module we're going to look at is for design for test. What you'll see in this module is that features will have to be added to the chip to help in manufacturing test. Typically the designer is involved in adding those features, and the designer that is aware that these features need to be added and is involved in actually adding them will end up in better designs. The reason for that is that because, as you will see, these features decrease the clock period, that is, make the design a little slower and make the design a little faster. So a good designer can be aware of these issues and can anticipate them early in the design process. The topics we're going to cover are as follows. I'm going to describe why we do this and illustrate to you how it is done. Then we'll talk about the dominant design for test technique, that is inserting scan chains to access internal nodes so we can test that they're actually okay. I'll discuss some other techniques, including functional test, memory test, and BIST, built-in self-test, and finally talk a little bit about how test insertion is done within the Synopsys environment, and some reference areas given at the bottom. So in engineering, in electrical engineering, everything is tested before it goes to a customer. This is not to discover design bugs, but to discover manufacturing defects, typically dust particles within the fabs, which is why the fabs are so clean. The test is done at every point in the assembly process. The first time test is done is when the wafers come out of the factory. And in fact, they are tested in wafer form, in their bare form, on giant test machines such as the one shown at the left there, in order to detect such manufacturing defects. I'm showing here a progression of images illustrating what happens. On the left, we have our test unit. This is a very expensive unit, many millions of dollars. What it does is successively apply test probes, which usually only go to the I/O pads, to the chip under test, and it has a very large amount of memory. That's in the box on the left. This memory stores test vectors that are applied to the chip and the expected results that are obtained from the chip. In the middle you see a test probe card. This is connected up to a set of leads. They go through those big bundles you see to the left of the machine that allows the vector stored in memory to be applied to and from the part under test. And on the right we have detail at the chip level. Here all the probes in that probe card have attached themselves to the chip and are applying vectors through the pads and reading results from them. You notice how big the pins are that are accessing the chips. Because of their size, they typically cannot operate at high data rates, typically only something like 100 or 200 megahertz. So our goal in chip test is to have a very high probability of finding manufacturing defects. These are caused by dust particles, which interrupt the marks that are printed through photolithography in the factory. Sometimes also caused by fab control problems, such as getting transistors out of specification. They actually make themselves apparent typically as opens and shorts between wires, or opens in wires, and transistors or wires out of specification that are usually too slow. Now this is a pure overhead function. We are expected to sell chips that work. So we want to have a very high probability of finding these defects. However, the customer does not reward us for spending too much money on chip test. Thus, our goal is to get a very high coverage of potential defects, this is called test coverage, while minimizing the cost of finding the defects. And this is where the designer gets involved in terms of evaluating the different techniques in order to minimize this cost while having a high probability of finding defects. Now we'll note that the design for test features that are added to the chip for test purposes can also be useful in debugging the first chips that come from the factory. No matter how much verification has been done, these chips are the first chips in the factory do have residual bugs in them, and thus the first round of chips that are back go through what's called a validation process to find out what those residual bugs are, if they are in fact are any, and there are about half the time. This is referred to as validation, because it's not verification, that's the software aspect we talked about in the previous class. So the DFT techniques are useful in validation, but they don't exist mainly for that purpose. We just reuse them for validation. In addition, and I won't be talking about this in this class, but there are sometimes additional features added to the chip in order to help in validation that are not part of the manufacturing test infrastructure. For example, a lot of chips today have timing and noise measurement circuits on them, so as to detect if bugs are being introduced due to excess noise on a power rail or due to incorrect timing in a clock tree, for example. We won't be talking much at all about validation in the rest of these notes. We're going to focus on manufacturing tests because it has a big change in how the designer approaches design. The cost of test might increase the cost of the chip by about 40%. That is why we're very sensitive to methods that reduce this cost overhead. There are several reasons for this cost. The first is that we have to grow the chip a little bit in order to add the design for test features that we'll be talking about. And this growth is typically in the 5 to 10% range. To get it down to 5%, you actually have to apply a lot of sophistication to how you judiciously apply different design for test techniques. In addition, there's time actually spent on the test units, and we want to minimize this. That tester I showed on the earlier slide cost millions of dollars. Thus, if you spend even minutes on it for each part, you're accruing cost due to the amortized cost of the machine. So these are typical test steps. Sometimes before going to that big tester I showed in an earlier page, you go through what's called wafer screening. This is just to detect wafers that are completely out of spec and don't need to be tested further. And this is usually a very simple test using one of the test monitors that are part of the wafer. Then we go through die tests in the wafer form. This is the biggest cost adder, and that's what's being done on the machine that I showed in the earlier slide. After that, we dice out the chips, singulate them into individual chips, and package the ones that are good. Obviously, we throw away the ones that are bad. There's no point spending money on packaging them. We then test them again after packaging. Then they are assembled onto a printed circuit board, and some aspects of the board are tested again before going to the customer. At this point, we specifically test the interfaces between all the chips, and quite often we run some functional testing, that is, run some end applications on the board as partial further testing. In this class, we're going to mainly deal with die test in wafer form, because that has a big impact on the design of the chip, and particularly the design of the logic blocks within the chip. And I'm going to remind you that even though the cost of test might seem high, the cost of releasing a defective chip is much higher. You spent money on packaging, you spent money on distribution, and now you have to manage the part returns. All of those are much more than this cost of catching the defect in the first place. In addition, there are intangible costs. You get a reduction in customer satisfaction if the customer bought a batch of chips that are bad, or a batch of chips in which many were bad. And that can lead to loss in future sales and future profitability. So our goal is to discover the vast majority of potential defects at the factory. So we're going to talk in the rest of this submodule about the dominant chip test technique, and that is scan testing using the stuck-at fault model. And I'll explain what these are in the next few slides. But I'll remind you some other methods are involved. Functional tests, where you actually run intended end functions on the chip. Often this is done post-packaging, but sometimes it's done pre-packaging so as to reduce the cost overhead of scan testing. Unfortunately, functional testing it doesn't give a very high probability of discovering defects. The reason is you can't run every function and every combination of functions that the chip has to support. So it typically detects about 60 to 80% of defects. However, it can be useful to find some aspects of the design that don't have to go through scan testing, or to reduce the number of scan test vectors that have to be applied. Something that's been of interest for a long time, but doesn't catch on in a big way generally, is a built-in self-test. This means adding features to the chip to enable it to test itself. We'll talk about this in the second submodule. But built-in self-test has a very attractive feature that the chip tests itself, and it doesn't need that expensive test unit to do it. All you have to do is power it up. However, the area overhead is significantly higher than for scan-based testing, and thus it increases the cost of each chip more so than the use of scan-based testing. It is sometimes used in mission-sensitive applications such as aircraft, because quite often in aircraft avionics, particularly mission-critical avionics, you can actually apply these self-test features to test the chip every time it's powered up, and thus self-discover that the part is working or not before you go off and fly into the wide blue yonder with it. Similarly for missiles and other applications like that. Delay fault testing is also an important aspect. This is actually usually done at package test, though it can be done at die level test. What this is some tests that ensure the chip can run at required speed. It's called delay fault testing because you're detecting delay faults. That is manufacturing defects that are increasing the delay of a function more so than is anticipated in the design of the CAD tools. An example would be a wire that came out too thin. This would increase the RC delay of the wire and could lead itself to a delay fault, or a transistor that's out of specification. So to get all this rolling, you need what is called a fault model. That is a model for the fault that can be simulated in the simulator, so that you can determine the impact of a potential fault. There's a model for the fault that can relate itself to the logic of the chip. Actual faults are mainly shorts and opens, and transistors and wires that are out of spec. This is difficult to apply at the logic level. Let's say you had a net list of your chip, and you wanted to determine what the impact was of a short between neighboring nets. You'd put the short in, and you're trying to work out how to detect that short, and this can be very messy to model and simulate. Because of the messiness of that, in practice we don't use the actual fault models. What we use is a simplified fault model, stuck at 0 or stuck at 1. That is, we assume that the actual faults produce a behavior that is similar to a node in the design being stuck at a logic 0 or stuck at a logic 1. Think about it. If you have a short between two wires and the left-hand wire is a 0, then the right-hand wire will behave like this. If the left-hand wire is a 1, then the right-hand wire would behave like we're stuck at 1. So this kind of approximates how the real faults manifest themselves on the chip, and in fact works out very well. I'm not going to show this to you, but you can show that using a stuck-at fault model allows you to actually evaluate most shorts and opens, but the vast majority of shorts and opens. So this is a very useful fault model, and the one that's ubiquitous throughout design DFT. So what we're going to do is apply these stuck-out faults to our design to determine how we detect them. We want to be able to detect both stuck-out faults at each and every node in the design. That is, they can occur anywhere in the design, and we have to make sure that none of the nodes in the design are stuck at 0 or stuck at 1. To do this, we employ a set of algorithms that sensitize a node to a stuck-at fault, such as node D here, and propagate the presence of that fault to some output. And we apply these algorithms to all our combinational logic blocks within our design to work out what vectors we need to apply at the input and what vectors we expect at the outputs in a defect-free chip. So here's an example here. What I want to do in this example is detect that node D has a stuck at 0 fault. To do this, I need to drive D to 1. If I drive D to 1 and doesn't behave as driven to 1, then that means the fault is actually present. So I'm going to use this nomenclature, no fault dash fault. So what I want to do is drive D to 1. If it behaves as it goes to 1, that means no fault is present. If it behaves as it goes to 0, then the fault is present, and I'll get a different result on E. So the first thing I have to do is determine a test vector that drives D to 1, that is, sensitizes a stuck at 0 fault at D. And you can apply simple logic principles to work out some candidate test vectors. There are several possible test vectors, but in all of them, it's quite simple. To drive D to 1, B has to be 0. Actually, we don't care what A and C is in order to drive D to 1. So all the test vectors that will sensitize this stuck at 0 fault involve B becoming equal to 0. We then have to propagate the existence of this fault to E. So we need a test vector that will produce an error at E if D is faulty. So we want an error at E if D is actually 0 instead of 1. To do this, C has to be 1. If C is 0, then E will, there's a NAND gate. If C is 0, then this fault here won't be propagated. We need C to be 1 in order to propagate the fault to E. So C has to be 1, and we get this behavior here. That is, if there's no fault, both D and C are 1, that means E is 0 because it's an AND gate. Because C is equal to 1, we've now propagated a 0 at D to the output, causing a change in the output because of the fault. So the faulty behavior at E will be that E will be 1. Thus, if we inspect D after the test, we know whether this fault has occurred or not. So this is how we detect stuck at 0 and stuck at 1 faults within a combinational logic block. What I've done is illustrate what is called the D algorithm that can work out test vectors to apply to a design to sensitize and propagate faults. The way this works in its entirety with its extensions is we list the faults, that is a stuck at 0, a stuck at 1 for each node. We determine the vectors that sensitize the fault and propagate the detection of that fault to the output of a combinational logic block. We then compressed that list of vectors. We want that vector set to be as short as possible to minimize time on the testing machine. And there's various algorithms that do this, that eliminate overlap between test vectors so that we can produce test vectors that actually can detect and propagate many faults. And sometimes we even go in and remove test vectors that only detect one fault and propagate it, That is, we sometimes accept a reduction in test cost by reducing test time by eliminating these low-yielding vectors after compression. But our goal here is to get a smaller test vector set as possible that can detect a very high percentage of the stuck at 0 and stuck at 1 faults at the outputs of the circuit blocks. The percentage of the faults that are thus detected is called the fault coverage. This is a term we'll use throughout the rest of the class, the fault coverage. So this is the core of modern scan-based testing. However, I think you've recognized something. How do you possibly get the vectors to the inputs of the logic blocks and the vectors out of the outputs of the logic blocks? Any modern chip today has potentially hundreds of thousands of logic blocks, and we only have a few hundred pins that don't even touch the internal logic blocks, the vast majority of these internal logic blocks. So we need some technique to apply these vectors to the combinational logic blocks and observe the outputs from outside the chip, because we can't get them into the chip through some other means. We can't probe the wires in here, they're just too dense. We can't use E-beams to get the tests in or anything like that. We need some way to get the tests in and out. And the way this is done is scan-based testing. That is, this is our synchronous logic under normal mode of operation. At every positive edge of the clock, Q becomes equal to D. The vector passes through. So all combinational logic is surrounded by registers. With a register applying the result to the input, logic operates, presents the output to this output register, that operates. The idea in scan-based testing is replace the flip-flops in these registers with a flip-flop, what's called a scannable flip-flop. That is, we put a mux, a multiplexer at the input. Now we have two modes of operation. We have the normal mode of operation where the data passes through the mux to the Q. This is when mode is 0 to the top input. We have the test mode of operation where when mode is 1, we scan in up there, pass it to Q, and this happens on every flip-flop, passing from the neighboring flip-flop to the lower flip-flop through the appropriate input of this mux. That is, when we introduce this as a scan cell, we're building this register to not connect to the combinational logic, but to be a serial shift register. So by building this as a serial shift register, we can scan vectors in and scan out the result. These shift chains are then connected to the pins of the chips in order to allow the external test equipment to get these vectors in and out. So this is the idea during scan-based testing. Step 1 is we serially scan in from an external pin the test vector we're going to apply to all the combinational logic in the chip, because all the logic is connected up in one or more scan chains. By the way, this will be happening on the right-hand side as well to present to the logic to its right. I'm just not showing that. Remember, the test equipment can't operate at the full clock rate. So this is done at the clock rate of the test equipment, usually a few hundred megahertz. We then operate the chip for one cycle. That is, we change mode to the normal mode of operation. We just clock one clock on the chip to actually operate the combinational logic. This will be applying the test vector we work out in the D algorithm to each and every logic block in parallel for the entire chip, getting a result into the registers on the right hand side. Typically this is done at the test speed of the logic tester, but it can also be done using the on-chip clock that's pulsed for one clock. This allows you to detect delay faults, because if there's an incorrect delay in this logic, you'll detect it, because this transfer to this transfer is happening at the normal clock rate. We then scan out the result and compare it in the test equipment to see if it's what we expect to see. So the registers are set back into the scan mode to operate as a serial test register. This also operates at the tester clock rate. This permits all the combinational logic in a design to be tested. And we test the flip-flops themselves through the scan chain. That tells them they're operating correctly. By the way, you'll notice we've increased the size and increased the delay of the flip-flops that are in the scan chains. This is one of the costs of adding design for test logic. And typically in logic synthesis, you've already worked out which logic is going to be scanned and which isn't during logic synthesis to make sure you account for this timing correctly. The test quality is measured by a factor called the test escape. This is the chips that get out of the factory that actually have a defect in them that you did not discover. Of course, you want this to be very low because it's very expensive to handle those chips when a customer detects that there's a defect in them. This can be calculated by this equation here. Test escape is 1 minus the yield raised to 1 minus the test coverage. T is the fault coverage. Y is the yield. That is the percentage of parts that are actually good. So for example, if the yield is 50%, which is kind of low, it's typically higher than that, and the test coverage is 95%, what is the test escape? We apply this equation and it works out to 3%, which is pretty high. 3% of the parts going to the factory are still defective and you haven't detected that. And by the way, if you just use the verification vectors from your Verilog test fixtures for test coverage, let's say this gives an 80% coverage, which is just in the high range actually, the test escape then would be 13%, which is abysmal. So that is why we have to add these test features. We just can't apply normal functions to the chip. It doesn't detect a very high percentage of the actual faults. So typically, the fault coverage is above 99% to give acceptably low test escapes. So generally, we apply what's called a full scan technique, where each and every flip-flop in the design is connected to a scan chain. However, there are mechanisms by which you can leave some flip-flops out and still get 100% test coverage. Basically, if you have a circuit, such as on the bottom here, where this intermediate register simply passes through the logic values there to the logic values there on the pulse edge clock without feedback around it, then you don't have to scan this. What you have to do is, for purposes of working at your test vectors, ignore this because it just passes through the results. Apply test vector there. 2 clock cycles later, get a test result there and scan that out. This is called partial scan and it's fairly common. The complexity is that some of your logic has to be operated in this 2 clock cycle pulse rather than 1 clock cycle pulse. So it complicates the test sequencing of how you get things done. You would do this in separate test sequences. But it can be done. What it does, it reduces the overhead of having all your flip-flops being scannable. So these flip-flops are not scannable. Often in addition, there's methods to eliminate scan from the flip-flops in the register files and other large blocks like that, which I won't go through. So that brings us to the end of this particular submodule. The main points I want to cover. Every chip has features added to it to permit the chip to be tested before leaving the factory, and the designer is involved in inserting the features because they impact the clock cycle time in the area. Those features are used to detect the presence of manufacturing defects and faults, not bugs, though they can be useful in debugging the hardware. The main fault model that is used is stuck at 0 or 1 fault model, where the fault manifests itself as each and every logic node possibly being stuck at a logic 0 or logic 1. We work out a set of test vectors. We apply CAD tools to work out a set of test vectors that sensitize those nodes to the fault that is driving the other direction and propagates an erroneous output to become an erroneous output at a combinational logic output. The flip-flops are then configured as scan chains to write in the vectors and read out the results. So thank you very much. The next submodule will look at memory testing and built-in self-test.